Hello, everyone. My name is Allahkaram Shafiei, PhD research students under supervision of Jakub Mareczek and Slava Kongerso. Thank you so much for giving me this opportunity to talk about my published paper journal about tree-level and multi-level optimization using monotone operator theory. My, my slides is bi-level optimization, tree-level optimization, algorithm and assumptions, convergence analysis, convergence rate of analysis, examples and application, and extension to multi-level optimization. First, let's talk a bit about bi-level optimization. Bi-level optimization has a nested structure, like, for example, for two level. Here you have upper level and lower level. Upper level and the name is leader, and lower level the name is follower. And the minimization of these objective functions depends to the solving of these lower level optimization problems. Tree level and bi-level optimization or NP-hard problems due to the involves solving two independent optimization problem where the solution to the outer or upper level problem depends on the solution to the inner or lower level problems. This nesting create a complex decision-making structure, making it computationally difficult to find the main optimal solution efficiently. Here is the structure of tree-level optimization problem. You have one objective function, omega. You want to minimize this objective function over X star, where X star is a set of minimization for composition of two SMOS and non-SMOS function. F1 is SMOS, G1 is non-SMOS. Also here, Y star is a set of optimal points of composition of SMOS and non-SMOS functions. Yeah, here you can see our paper was published in the Journal of Mathematical Methods of Operation Research. For solving this tree-level optimization, we want to use the proximal gradient method for making the algorithm to solve a tree-level optimization problem. Proximal gradient method is an extension of gradient descent method. Gradient descent method already was applied for just SMOS functions. But in our case, we have the composition of SMOS and non-SMOS, which proximal gradient can be applied for the part of non-SMOS functions. In compare with another methods, the rate of convergence, for example, for Fisto methods, is faster or methods, but this method cannot be applied for tree-level optimization problem because of due to the complexity of nested structure. This method, I mean the Fisto method, cannot be applied to solve the tree-level optimization. Because of this, we used the proximal gradient methods. Proximal gradient operator for the composition of two functions, f is smooth and g is non-smooth, is the following. Here you can see. And the proximal here, the proximal for function, non-smooth function g, is a set of minimization points of these functions. Now we have the main property here, which already has proved, which the fixed points, all fixed points of this operator is a set of minimization of this composition, f plus g. Our algorithm is like this. We can make the proximal gradient for Trilevel. We have four generated sequence, yk, zk, nu-k, and xk. And xk is a linear combination of these three sequence. In the next slide, we have some critical assumptions over the step size, which these assumptions guarantees the convergence of generated sequence by the algorithm, and also later the rate of getting the rate of convergence. Assumption 2 is like alpha k going to 0, and the summation of alpha k is infinite. Assumption 3, you can see here the limit superior 1 over alpha, and this absolute difference, it should be bounded. And the limit superior of this fraction should be 0. Okay, this lemma say us the generated sequence by the algorithm is bounded when delta is infinite. Let's get back to the last slide here. Delta is a limit superior of this fraction, beta k over alpha k. And we have this result here. Here we have a quadratic growth condition. Just this condition is over the x star. I mean, you suppose that phi1 grows quadratically or globally away from the part of minimization set y star. Y star already we proved that is all fixed points of operator W. So you have here phi1x is more than phi1 star plus mu over 2. Here is a distance of the square distance of x and x star. And omega 1 is a ball around of 0 with radius cx0. Here is a main theorem for convergence of sequence xk generated by the algorithm when you have the assumption 11 and delta is 0. You can say xk is a convergence to the x star belong to capital X star. This means that you have X star is an optimal point of the main objective, this outer level, Trilevel optimization problem. The next results happens when you have assumption 11, and in this case, you have delta is infinite. In this case, you can say xk is bounded, and also xk is a convergence to the x star belong to big X star. Also here, we want to say how to proceed with convergency under some error bound condition. Error bound condition, the definition is here. You have this operator W from X to X, and fixed points of this W is non-empty. We say that W is a bounded linear regular when you have this condition. Now, these results say us when delta tilde is infinite and you have assumption 2, 3, and 4, you can say xk is bounded, and moreover, you have you should assume that xk is bounded, and you have these following assumptions. W is a bounded linear regular, and you have this assumption over step size limit superior beta k square over alpha k is 0. Then you have xk is a convergence to the x star, and X star, is the minimizer of omega over the big omega. Also here, you have this result when delta is finite. Together, you have assumptions 2, 3, and 4, and assumption A2 from theorem 19. And also you will assume that assumption 11 holds for omega in place of X star. Then xk is convergence to X star. The next lemma, which is coming from the Sabach and Stern paper 2017, this is an important lemma for talking about the rate of convergence for a tree-level optimization problem. If you have fixed positive m here, and you have a sequence non-negative sequence ak, which the first number here is less than m, and then you have this condition. So you can say ak is less than mj over gamma k. So by this lemma, we can obtain this upper bound for a difference of these sequences. Norm xk minus 1 is less than this term. Also, norm zk minus xk minus 1 is less than this term. All this happens for each x belong to fixed point of w. Here you can see the rate of convergence for the middle level of tree-level optimization. When you have xk, nu k, and zk, and yk are the sequence generated by the algorithm, the main algorithm, and you have alpha k proposed by already the paper mentioned, then you have this upper bound, the rate of convergence, for the difference of this term. And next results also is about the inner level, about the convergence rate for inner level. You can see here. And here, the 55, the rate of convergence for outer level, the main objective of omega. So let's point out the two examples and applications in machine learning. As you know that the structure of our problem is like smooth plus non-smooth functions. So the lasso class of functions which list absolute shrinkage and selection operator, you know, is widely applied for feature selection and regularization in linear models. In a trilevel framework, it can be extended to address multiple decision levels. Let's point out here, outer level selects a robust model that minimizes the prediction of error under the worst case condition, and middle level choose regularization hyperparameter lambda 1 to minimize the lasso loss, combining data fitting and penalty for sparsity. Inner level solve the classical lasso objective to select the coefficient beta, minimizing the sum of squared error and L1 penalty. You can see the structure of problems here, the minimization of omega over x star. Here is the x star is a solution obtained from the middle level, which is the set of minimization for phi 2 and function phi 2, which is, you know, the composition of smooth and non-smooth function. A smooth function is here, the square of this difference, and non-smooth is a norm 1 beta. And also for the inner level, you should solve the lasso problem like y star is a set of minimization for phi 1, and phi 1 is a composition of two smooth and non-smooth functions. And you see here the trilevel for support vector machine optimization problem. Outer level is a minimization of classification error under uncertainty. You can see here. And X star here is the set of minimization for phi 2, and phi 2 is this composition. The first term is smooth, all you know that about this, and the second term is non-smooth. Yes, you can see here. An extension to multi-level optimization. Here we extend Trilevel to multi-level convex optimization problem involving an arbitrary number of nested minimization problems, where you can see here the objective function, the main objective function here is omega, and the first level is the minimization of f1 plus g1. The second level minimization of f2 plus g2, and then fn plus g1, gn. So the iteration for solving this multi-level optimization is this iteration with a step size of alpha k0, alpha k1, and so on, alpha kn. Also here we use the proximal operator, proximal gradient operator to solving this algorithm. Here we have the main lemma, which when you have the set of finite set of non-expansive mappings, the intersection, the fixed point of linear combination of this operator is the intersection of fixed points of each operator. And we note that the operator should be non-expansive. And also, you know that all operators in a proximal gradient method are non-expansive. So we have this, we take these assumptions, our step size of multi-level optimization, you can see here. And then take this assumption quadratic growth condition for the first level of the multi-level optimization problem. We see that phi1 should be more than phi1 star. Phi1 star is the optimal value of phi1. And here is a distance of x and xn star. Xn star is a set of minimal points of n layer of multi-level optimization problem. Okay, we have here the geometrically view of the set of points in x star n is as follow. X star n, if has a non-empty interior, then x star n is an intersection of all fixed points of Ti. If you have assumption P2, then the sequence xk generated by the algorithm is bounded. Also, we are in position to get these main results about the convergence of sequence xk generated by the algorithm. That when x star has a non-empty interior and you have this assumption over step sizes, then xk is a convergence and you have this, the xk is a convergence to xn star, which xn star is a minimal point of the main objective omega in the structure of multi-level optimization problem. And then here you have if assumption P2 hold and delta star is 0 together with assumption 31, then xk generated by algorithm by the main algorithm is convergence to a unique xn star belong to big xn star. You have this, and xn star, as I pointed out already, is a minimal point of the main objective omega. Here is the rate of convergence. The rate of convergence for multi-level optimization problem, where you take yki as this operator at this point. We take care which xk is generated by iteration in the multi-level optimization problem. Already we talked about that. And then you have the rate of convergence here for the difference of this for the phi 1 yk. The YK1 has a rate of convergence like this. And then phi I for each level, we have this rate of convergence, 1 over k. And here, for the objective functions, we have rate of convergence, this. And this is a bit references which we used in these slides. And thank you so much for your attention.